move, I just think this is so much easier to understand. So this is exactly the same as this, except I've topologically moved things around. Like, I think. Can you see that? So this is supposed to be the same as that tree, this is supposed to be yeah. Right. It's just prettier. Okay. Yeah, so this is a concrete example. I've computed the inner product between this basis state, where this is a 1 being fused in this direction, and this basis state where, so these are the same, 0, 1, 1, 1, 0, 1, otherwise the inner product would be 0. This is the same, otherwise the inner product would be 0. But the internal states are different, and in fact the internal direction is different. And so since this is one f to get from here to here, you get just a factor of 1, 1. Get this guy here from a 1 to a 0, which is 1 over square root of tau. So that's that. So I mean, these are things that you can actually compute by hand. It's not magic. It's just something you can do. Mark, it's usually a bad idea to mix bases. Yeah, just like with qubits. With qubits, you can work in any orthonormal basis you want, like the 0, 1 basis or the plus minus basis or whatever. Everything's fine. The same with here. You can work in this basis, this orthonormal basis. That's fine. But you don't want to. That's a bad idea usually. It makes sense, but it's just weird. The same thing's true with the anyons. Like, it does make sense to talk about superposition between things in different bases, but that would be really weird. So you always use you fix one fusion order, and you use that for your whole computation. Or at least you'll keep it the same with any line of your computation. You'll only use one basis. Okay, so I do have other anion models here in the notes. What's the interesting ones? So Z2 is not an interesting model. So here the particles are 0 or 1, and you just get the XOR for this sum. And you can't store any quantum information here because, well, let's see. You can. So 0, 1, 1, 1. Say that's the quasi-particles. And here I'm fusing from left to right. It's completely deterministic. So 0 plus 1, this edge has to be a 1. This edge has to be a 0. This edge has to be 1. This edge has to be a 0, and so on. Or 1, and so on. Because there's only one possible fusion outcome. And so you can't have superpositions over, like you can't have this plus another term. But if you fix these to be all the same, like all ones, then you just get a one-dimensional state, which isn't interesting for quantum computation. So for physical reasons, we were interested in the case where they're all fixed.
Never mind.
Okay. So that's boring. SE2K is, oh, so here I have it here. SE2K, this is, SE2 is spin truncated at level K, I think. So yeah, here's the fusion rule. A fused with B gives you C, where C could be anything between A minus B and up to that that expression. Oh, so this is, I had the Ising model run. So in the Ising model, 1 cross 1 is equal to 0, not 0 plus 1. But everything else is the same. So 1/2 plus 1/2, 1/2 times 1/2 would be 0, 0, or 1. So this is a very interesting model. These are the R numbers for this model, either the 5 pi I over 8, either the I pi over 8. So if you swap 2 1/2s that merge to 0, you get this. If you swap 2 1/2s that merge to 1, you get that phase. And it's just magic. That's what works. And the F matrix is given by this 2 by 2 matrix, just like the towels in 1 over square root of 2 towels. It's interesting though. Like this looks like a Hadamard gate. That's not a coincidence. Actually, in the Ising model, and also here, like e to the 5 pi over 8 and e to the I pi over 8, the difference is e to the 4 pi over I over 8, right? Which is just -1. Yeah. So this is actually like a Z gate up to a global phase. This is like a Z gate, and this is like a Hammer gate. That's not a coincidence. That's in the Ising model. The only gates you get are Clifford gates.
Sorry, is that the Z gate or the S gate?
Minus Z gate. That's right.
The S gate?
Why?
The
E to the 4
5
pi